Okay, so let's get started. Today we're going to look at the speed of sound. So here we have a graphic representation of a sound wave. Something I want to point out is that sound waves are always going to be longitudinal and mechanical. So they're always going to move parallel to the direction of the energy. It's going to cause the particles of air or whatever medium we're referring to vibrate, and that vibration is going to be carried across the air through these compressions and rarefactions until the sound is heard by the observer. If we were to represent that as a transverse wave, which it is not, but if we represented it as a transverse wave, it would appear like this. Remember that a compression corresponds to a crest. But bear in mind that all sound waves are mechanical and longitudinal. So here we have a table that lists the different materials and the speed of sound, the approximate or average speed of sound of these materials. The first two are gases, and we have air and then helium. And if you go down the list, what you can see is as you increase the density of the substance, the speed of sound is actually faster. So solids are going to have faster sounds, faster velocity of sound as it moves through those materials. And then gases have the slowest. We are more familiar with air because that's how most of our sound is transmitted. We're surrounded by air on Earth all the time, and so we're most familiar with that. But you can see here in steel, speed of sound is 5,000 meters per second. Here, air is around 346. That's an average. But to find the precise sound of air, we have to actually use a mathematical formula. So an average is about 346 meters per second. To find that speed precisely, we have to use this formula. So 331 plus 0.61 times temperature. That temperature has to be in Celsius. So you can imagine that if you had 100 degrees Celsius, which would not occur, but theoretically if you did, 100 times 0.61 is going to be 61. And so in that case, you would add 61 to 331. But let's look at this example. Let's say the temperature of the air is 30 degrees Celsius. So again, it's 331 plus 0.61 times temperature in Celsius. Now you could say 61% of the temperature in Celsius. That's the same thing. But if we take the temperature, which is 30, and multiply by 0.61, we're going to have 18.3. So in this example, if I have the temperature at 30 degrees Celsius, I'm going to apply this formula, and when I simplify 0.61 times T, which is temperature in Celsius, I get 18.3. So I take that 331, which is right here, and I add 18.3, and my overall speed of sound in this temperature is going to be 349.3 meters per second. Now, that's a little bit above the average speed, but to find it, again, you take 331 times 0.61 times the temperature in Celsius. So when we talk about the speed of sound, it's going to depend on three main things. First of all, the actual material that we have, we call that a medium. The density of that medium, remember that solids, the speed of sound moves faster through solids. And then the temperature of the medium. The hotter or the warmer, the greater the temperature of that medium, the faster that sound is going to travel. So go ahead and complete your fever form, and if you have any questions, let me know.